The introduction to Dynamic Analyst always begins with the Belt Analyst program. A designer must design the conveyor, size all the components, calculate all the friction factors in Belt Analyst before you can ever start with the Dynamic Analyst program. There is also some preparation work that must be done prior to running the Dynamics program. First thing is that there must be belt segments in between each of pulleys in your Belt Analyst file. You cannot run Belt Analyst if two pulleys are side by side in a Belt Analyst file. The other thing that we recommend is that the SEMA 6th edition version be selected to do your calculation. The SEMA universal method, as published in the 6th edition, is the only calculation method that is speed dependent. And since we are starting and stopping the conveyor and the speed's changing, we do believe the results in Dynamics is more accurate if your calculations are using the SEMA universal method. Once everything is correctly set up, from the add-ins menu, click the Dynamic Analyst add-in module, or F11. When you do this, it'll open up the Dynamic Analyst program. You can see an icon in the bottom of the screen that represents Belt Analyst. By clicking the icon, it'll take you back to Belt Analyst. If you click the new icon that's located in Belt Analyst, it'll take you back to Dynamics. No two pieces of information are input in two different places. So any inputs that you want to change, such as belt width, tonnage, speed, or any of the component data, you need to change those in Belt Analyst, so all the calculations are redone before you run the Dynamics program. If you use the buttons on the icons to switch back and forth between the two programs, the data will stay synchronized and stay up to date. To get familiar with the Dynamic Analyst screen, we'll now take a look at the tabs down the left side of the program folder. The first one is the Notes tabs, where you simply keep your project description, engineer doing the work, location of the project and description, and you can also put any comments in here that you'd like to show up on the printout, which is public comments, and if you'd like to put in comments that won't show in the printout, include them as private comments. The next tab down is labeled Drives. This is where we describe any of the dynamic characteristics of our motors and drives. That can be all the black information or the black data that's included in this is data that's been brought over from our Belt Analyst program, such as the 500 kilowatts or 1500 RPMs, full load torque, gear ratio, pulley diameter, etc. So any of these items that's in black, the only place you can change those is in Belt Analyst. So if you have to change any of those, click on the Belt Analyst tab and go back to Belt Analyst and change them, update that file, update all the calculations, and then come back to Dynamics. Anything that's blue on this page can be edited. The number of motors, the full load RPM of the drives can be changed to adjust the slip in the drives, and all of the speed torque curve characteristics can be modified at this point. So if we change the data in the motor speed versus torque columns in the grid, it'll interactively change the drawing of this motor speed torque curve to the left. The next tab down represents brakes, if there are mechanical brakes in the system. We'll go over this in much more detail later, but we can define the rating of our mechanical brakes and the efficiency. In other words, if the brake pads are worn, we can adjust the efficiency, which affects the effective brake torque that's being applied to the belt. And we can also adjust the control functions in the brake, which is the second tab at the top of the form, which we'll go into later on. The next tab down is holdbacks or backstops, and any drive location, any drive that's been identified in the belt analyst file is a potential location for a backstop. And in this case, we only have one drive location, so we only have the option to click the backstop at this location. If we have a backstop on a non-driven pulley, then we have to define that pulley in belt analyst as a drive pulley, even though it may not have a motor on it, so that we have the option to click that location as a backstop location in the Dynamics program. The next tab represents the Takeup, and again here we can define the dynamic characteristics of a Takeup. It can be a gravity Takeup, a mechanical Takeup such as a winch or hydraulic cylinder, or it can be a fixed Takeup, in other words a fixed pulley. We also have various options in this to define the speed response curve of the Takeup. In other words, if we have a mechanical winch, it may only be able to go so fast before the torque either increases or decreases depending on which direction we're traveling. So we have a couple of tabs here which gives us the ability to define those mechanical characteristics or further control how the Takeup might respond in various scenarios. The last tab we need to talk about is the one that defines our simulation parameters. We start off by defining how long we want the simulation to run. In this case 30 seconds, which represents 1,500 simulation steps. Those simulation steps, of course, is based on the simulation time increment in seconds. In this case, the program has decided that it probably needs about a 0.02 simulation time increment. That can be changed, but we do recommend it be somewhere between 0.01 and 0.05, and the program will recommend a value for you, which in most cases will be satisfactory. The simulation time, you need to set that. The program will set that for you, so if it's going to stop in approximately 20 seconds based on belt analyst, then you probably want to run it for about 30 to make sure that everything comes to a stop before you stop the simulation. The minimum number of elements also the program actually selected in this case actual number of elements of 91. You can put in a different number here as number of elements. We would recommend at this point that you really don't change that too much and let the program select that for you. In the advanced course we might talk about the need sometimes to increase the number of elements, but in 99% of the cases you leave the number of elements as the program recommends. The plot interval, we like to generally plot for our graphing purposes points about every 0.1 second, which makes a nice animation speed. In this case, if our simulation time increments 0.02, that would be a plot every 5 simulation increments. The last item here that's important is the Autotune button. This is a finite element based program, and the Autotune button will automatically go through the simulation, make several runs, and will automatically tune the damping multipliers. There's 3 damping multipliers in the program that's used, and so that you don't have to figure out what those are, the program will do that for you. So the next thing we'll do is click the Autotune button. It's very important the Autotune button is first pressed whenever you start a new file or make any significant change to your belt analyst file in order to reset the damping factors in the program. You'll see a black box pop up and calculations being made, and you'll see a power plot that pops up periodically on the right side of the screen. This iterative process is where the program is actually running the dynamic code, the FEA code, multiple times. It's evaluating the results. It's making changes to the damping multipliers. There's 3 of them in the program. And you'll see here that it is adjusting this single damping multiplier. So you'll see what the final result is. There's 3 values being changed internally to the program. Only one is being shown here as a ratio to 1, which is our baseline damping. Generally this number in this case ended up 0.85 damping multiplier. Generally it'll end up between 0.7 and 1.1, somewhere in that range. If you're in cold temperature, for instance, there might be more damping in the system. It might be a larger number. If it's summer conditions and low friction calculation that you're doing, you may end up with a smaller damping multiplier. That can be changed. You as a user can change that number. We would recommend, to feel very comfortable doing that you just use the value that the program generates for you. Since we start with a belt analyst file, the data that we're bringing over is our running steady state normal condition. So the first thing we do in Dynamics is we have to stop the conveyor belt. So you can see in the upper left hand corner of the screen we have highlighted our stopping condition. We can never do a start of any belt until we've previously stopped it. The program then saves the conditions of a stop belt, and then we can go do a restart. So we at any time can hit the simulate button on the right side of the screen. The black box, which indicates the execution is taking place, will pop up. The time will click off as the calculation is being made, and then the data will appear on the right side of the screen as a tension diagram and a velocity diagram. There are green buttons at the lower right hand corner representing play, pause, stop, and rewind that let you watch the animation, in this case a stopping animation of the belt going from full speed to stop. We can also zero in on specific points on the conveyor. Look, in this case, the tension in the belt at various points, in this case the 3 pulleys in the system. We can look at the belt speeds, power, torque, drive slip, take up, displacement and velocity, and belt sag in the system. Again, we'll hit the play button and we watch the time click off as the belt drops from 3 meters per second down to 0 and goes back into a steady state stop condition. Once we've successfully stopped the belt, we can click on the starting tab, highlight starting, and now we'll have to identify how we want to start this conveyor up. So we'll go to the motor controller and we'll pick a line start, just across the line start, and we'll go and make sure we have enough time here to get the start started. So we select the 30-second start. We hit the simulate button and we generate a restart in the system, and now you can see the conveyor going from 0 to 3.3 meters per second as we watch the tensions in the belt and the belt velocity change as the conveyor goes back up to speed. Again, during startup, it's just like stopping. We can look at the belt tensions, the velocities, the power, torque. We can look at potential slip in the conveyor, the take-up displacement and velocity, and sag between the idlers anytime in this system. So again, the startup of the system, we have the opportunity here to redefine the motor characteristics, brakes, or the take-up, redefine the simulation parameters such as simulation time, etc. We do want to keep Autotune the same. We don't need to Autotune. The stop and the start is the same, so once we've auto-tuned for our stopping condition, we use exactly the same number for our starting condition. So if we recap the process here, we do our initial running conditions in Belt Analyst. We come over to Dynamics module. We click the stopping button. We change the parameters. We do the calculations for stopping. Then we save that. The program automatically saves that data. We switch over to starting. We can modify the component data to represent our starting conditions, and then we look at the starting characteristics and make sure everything is proper and works correctly.